All right, so we've seen that provided the charge distribution of interest has some type of symmetry to be leveraged, you can use Gauss's law and just render a solution very quickly when an application of Coulomb's law might take much more time and effort. And there's really no mystery to how to choose the Gaussian surface. If the charge distribution has spherical symmetry, you'd use a spherical Gaussian surface. If it has cylindrical symmetry, you'd use a cylindrical surface. And in this case, I really struggled trying to draw this infinite planar slab. You'll see in the case of planar slabs, you often use a Gaussian surface that I like to call a Gaussian pillbox, and I'll show you why in just a second. But this problem, this problem says you've got an infinite slab of charge with charge density rho. I guess we don't care if rho is positive or negative. And you're asked to calculate the field both internal to the slab and the field external to the slab, right? So let's go ahead and do that. Let's remove that graphic so that we can have some space. And now, to do the analysis, let's imagine that we were looking right down the x-axis, and what we would have seen then is this this slab of charge which extends in all directions. It does have a midplane. If this is the z direction that we're looking at, if this is the z direction, then this point was plus z0, and this point is minus z0. So that's the slab that's 2z0 thick. So before we just try to take off, let's talk about what kind of electric field we expect. Because the charge distribution is the same everywhere in this xy plane, the electric field is everywhere going to be an electric field that's dependent on z. It's always in the z direction. The electric vectors are always, in this picture, they're always vertical. And so that's going to give us some idea about how to choose the Gaussian surface. Let me do that right now. This problem asks for the field interior to the slab and the field exterior to the slab. So for the field interior, I'm going to draw what I've called a Gaussian pillbox. And I'll draw it right here. You know, it's a little small. Let me kind of pull that out and look at a bigger version of that now. So there's the Gaussian pillbox. It's got a circular cap on the top and the bottom, and then lateral sides around it. So in this case, the reason why this works out very well for us in this problem is first and foremost, by the symmetry of the problem, if again the electric field is in the z direction and rho is positive, then the electric vector on this side, the positive side of this midplane, is going to point away, and the electric vector on the underneath side is also going to point away. If rho was negative, then both of these vectors would have pointed towards the charge distribution. But in all cases, again, the electric vector is only going to have a z component. So if that's the case, you know, what's going on at the midplane? The electric field is this way, above it, this way, below it. It's pretty clear that at the midplane, the electric field has got a value of 0. All right, so let's make use of that. Let's set up this little Gaussian pillbox on so that the bottom cap is on the midplane. And we know there the electric vector is 0. E is equal to 0. Right? So if that's the case, the flux through the lower cap is also 0. if we just let this point right here be z high, so this is now the midplane z equals 0, this is the height z above, let's look at what the flux is through the lateral sides. To do that, what we have to do is to pick up a number of different little differential area elements, and you would see that the normal times the size of that is everywhere perpendicular to the electric field, because the electric field is always in the z direction. And that means that this little differential flux is got a magnitude of, well, its value is E dA cosine theta, and if theta is equal to pi over 2, cosine theta is equal to 0, and the flux everywhere through the lateral sides is 0. There's no electric field getting out the lateral sides. There is electric field, however, on the upper cap. And so how would we analyze the upper cap? We're going to call that electric field E sub z. We're going to call the area of the upper cap A. That's the flux through the upper cap. And Gauss's law says that's equal to the charge enclosed divided by epsilon 0. Okay, so now we ask ourselves, well, what the heck is the charge enclosed? We were given at the outset that this charge slab has a uniform volumetric charge distribution, and so Q enclosed is just that uniform charge distribution times the volume of this little pillbox. And this little pillbox has an area at the top. I called it circular. It doesn't need to be. It just has to have an area A, and it's got a height Z. Yeah? So if we kind of combine these two things, you see E Z A is equal to rho A Z epsilon 0. These two A's cancel, and the electric field is given by rho all over epsilon 0 times Z, provided Z is between Z0, minus Z0 and Z0. Yep. So that's the solution to the problem inside the slab. If we want to go outside the slab, we're going to just extend this little pillbox to a point above the slab. So now here's our value Z, right? We'll be careful to note as we get on that Z is greater than Z0 in this case, but it's absolutely the same analysis. There is no flux through the lower cap because there's no electric field there. There's no flux through the lateral sides because the electric field is traveling everywhere parallel to the sides. And again then, the electric field up here is, we're going to call E sub Z. If we multiply it by the area A, we get the flux through that upper cap. That's equal to the charge enclosed, and that's equal to rho times A all over epsilon sub O. This time not Z, because the only fraction of this little pillbox that contains charge is only Z0 high. All right? And so, again, when we cancel the A's, we get E sub Z is equal to rho epsilon 0 Z0. And that's the case for Z, I'll say Z greater than or equal to Z0. Yeah, we've just done the solution for above the plane. Exactly the same solution for the Z values below the slab. All right, good enough. Again, just to kind of make use of the proper Gaussian surface to fit the charge distribution that we're dealing with. All right, more later.